All right. Well, hello everybody. Today I'm going to be talking about promising paths to alignment. And let's get just right into it. There are none. Thanks for coming to my talk. I really hope you enjoyed. Are there any questions? All right. Obviously I'm joking. But to every joke, there is a bit of truth. And the bit of truth in this case is that in my opinion, we don't currently have any kind of approaches that obviously are going to lead to a solution to the problem in general. That doesn't mean there's no approaches, but I don't think we're at a point where I can point to a direction and say, yeah, this is going to lead us where we want to be. Surprising to me, I seem to be among the more pessimistic people, just a bit for your calibration here in this regard. So I was recently at EA Global, and I talked to a bunch of alignment researchers and a lot of people in the field about their timelines and their probabilities of things going bad and so on. And I was quite surprised to see that I was definitely among the more pessimistic people. That many, maybe even most people had probabilities of things going well, well above 50%, which is definitely not the case for me. So I was invited to give this talk to talk about paths that I find promising, and I'm going to do that. I'm going to talk about some of the things that I do think are promising and might be interesting to work on, to look into. But from my experience at EA Global and more generally talking to people, I think that a more valuable thing perhaps for me to talk about is a little bit about the reasoning why I think the problem is hard. I will give you a bit of the generators of what makes this problem particularly different from other problems. I'm not trying to say that no progress has been made, unlike certain other people. There is progress, and there are promising approaches that I think have helped us deconfuse these methods, these questions, and so on. But I do think that there is a tendency sometimes for certain people to, I think, miss the core of the problem and why it's hard. And I would like to talk a little bit about that, and then I will also talk a bit about more concrete directions that I find promising. So I'm not here to give you the bad alignment bingo takedown or whatever, right? There's always these classic, bad approaches that show, everyone comes up with when they first hear about alignment. This is not really what I mean here. I think there are obviously, silly solutions, like just use Asimov's 3 law. That's a bit silly, right? But I think there is a more subtle case of why I expect alignment to be hard that sometimes I feel even EAs don't fully grok, but I think it's very important to understanding the core of the problem. This is especially important because of what I've dubbed substitution hazards. And I think there is some technical word for this in the psychology literature or something, but I couldn't find it for the life of me. If anyone knows the correct word for what I'm about to describe, please tell me. It's this common psychological phenomena where people faced with a hard problem will instead substitute it with an easy problem, make progress on the easy problem, and then think they made progress on the hard problem. So this is a very common phenomenon in humans. Of course, if you were perfectly rational and you track all of your, belief systems and how you make progress in various problems, there's no problem with this. Making some progress on an easy problem can be useful. But the problem is that the way humans tend to work is you tend to overestimate how much that was actually useful for the hard problem. A classic example of this is hard problem, solving climate change. Easy problem, recycling your trash. Solving climate change is really hard. There's it's where do you even start with that? And then you might be tempted to say, well, I could, recycle my trash. That's a step in the right direction. And that's fine. That's great, if you make sure that you're aware of the amount or small or large amount that actually contributes to solving the problem. No problem with this. But there's a classic problem that can happen where by doing something, the human brain will kind of be satisfied. It's I did my part, so now I can relax, I'm not expected to do more than this. And that's nice and all, but you still didn't solve climate change. And someone has to do that. So that's why I think it's really important to understand what is the hard problem of alignment. There is a temptation to look at easier versions of the problem, make progress on those, and then say, oh, this will scale, we've made progress, which might be true. I want to make very clear that might be true. A lot of science is done this way. A lot of science is you first solve simple test cases and then you start to slowly, generalize your solutions. I'm not saying this is always bad. I'm just saying this is a problem that you have to very much be aware of, and you have to keep in the back of your mind what the actual hard problem is you're trying to solve. Alignment is not just another technical problem, is what I'm trying to claim here. I'm going to justify what I mean by this and why I think this is really important. The shape of the problem is particularly wicked in the sense of a wicked problem. It is shaped in such a way, the kinds of things that need to be done to solve it, and the obstacles we face are those that our species are just particularly bad at solving. It is really a very cruelly designed problem. Therefore, the kinds of problems our civilization, our science tends to be good at. And I think there's like two main reasons what make this problem so hard. There's others as well, but I'm going to focus on two in particular. The one is just that we're dealing with superintelligent optimizers. And superintelligent optimizers are a class of object that we are just not familiar with. When we find a new chemical, or we find a new star, or we find we design a new computer language, these are objects that we understand. Like, these are objects we've encountered before. We have a lot of theory. We have even just like a gut instinct of how these kinds of things work. There is no superintelligent optimizer currently existent, has never existed in the entire universe. We're dealing with a whole new class of objects that has new kinds of properties that we are not familiar with, that will cause many of our normal methods to not work. We have a whole new world of failure modes that our current methods of science are just not set up to deal with effectively. I'll say more about that in a second. And the other one is coordination. So, humans are social animals. We're incredibly good at coordination compared to chimps, but are we really good at coordination? I'm going to say is frowny face. Coordination is hard, and coordination might be really important to solving this problem. It is solvable, though. This is really something I wanted to emphasize. It's very easy to go all doom and gloom and be like, oh yeah, we're all going to die, everything's terrible, we can't coordinate, we can't solve the problem, blah, blah, blah. I want to really stress, I fully believe the alignment problem is a solvable technical problem. If we had enough time, we had enough smart people doing good theory, doing good science on this thing, this is a problem that can be solved. There is no law of physics that says you cannot design and construct and run a aligned superintelligence. This is something that our physics allows. We have no reason to believe otherwise. Whether we will do so in practice, though, unfortunately, a different question. So, if you take anything from this talk at all, make it this slide. This is, I think, the most important core of what I think is important to understand when trying to solve the alignment problem. So if you check out after this, that's fine, whatever, right? But please, this thing I think is really at the core of the problem, is that very common thing I hear, especially when talking to like smart Silicon Valley engineer type people, but even some alignment researchers, they say something along the lines of, we'll just figure it out as we go along. They'll say, we've had hard problems before. We already have to build, like nuclear reactors that don't melt and bridges that don't fall down. This is just another problem like any other. As we develop more and more of these systems, as we get more used to them, we see them fail in different ways, we'll slowly, iteratively, learn how to control and make them safer over time. And I want to argue that that is not the case. And this is at the heart of why this problem is hard. There's an entire new class of failures that our current methods of science are just not up to snuff to dealing with. In particular, I think one of the core problems is that optimizers are basically black swan generators. And our methodology of science, are like, Enlightenment era, Popperian, barely Bayesian understanding of how to do science is not good at dealing with, things that have many unlikely high impact events. And optimizers are exactly that. They're systems that can push reality into very unlikely configurations. This completely changes how things fail, how you should expect things to fail. There are some fields of research that do deal with similar objects. The closest is computer security. Computer security also deals with intelligent adversaries that can optimize and bring your state into extremely bizarre states then you have to defend against. There's a very strong connection between alignment thinking and what a good security expert thinks about, a good computer security expert. For most of history, we had this guarantee as humans that there was no thing running out there that is smarter than us, that is better at moving reality into strange, specific adversarial states than we are. Humans can design all kinds of weird things. I am currently talking into a brick of plastic and silicone that is beaming all of my words up, to people across the world. That is a very strange state compared to the average background radiation of the universe. It's a very weird state to exist as a biological creature and to have technology and do all these kind of things. These are all extremely low probability events, but because we're optimizers, we can push reality into these very low probability events and make them high probability, because that's the whole point of having an optimizer. And because we humans are used to being the only optimizers around of this strength, and there definitely are none out there that's stronger, all of our thinking of how security works, about how to do science, about the maximum damage that could be caused from a certain accident, are systems that were developed in worlds where this guarantee holds. It never was that we had to deal spontaneously with, some dog spontaneously becoming smarter than all humans combined, and we have to deal with that. It's just not a thing that happened. Our current methods of science, I'm going to claim here, depend to a very large degree on two things being true. We have to be able to do many repeat experiments and observe failure. There's a lot of iterativeness that goes on in most science and engineering. It's gotten better over the time as we've developed better and better theories, but very often in the history of science, experiment precedes theory. We first have to try many things. We have to build many steam boilers and see them blow up until we figure out thermodynamics. And the second one I'm going to claim is a problem is we have to be able to model things as well-behaved probabilities with few black swan events. Any scientist's favorite tool is the normal distribution. That's always what you want to work with. Whenever you're modeling any kind of system, you want well-behaved probability distributions you can reason about. Like, what is the maximum failure we expect to apply here? If you have a model of possible failures of your system, and you model it to say it's some kind of normal distribution, whatever, you have these vanishing probabilities on tail ends where you can basically assume that's never going to happen. But not all systems behave this nicely. This is why modeling the stock market is hard, is that the stock market very much does not behave like a nice normal distribution, and many other systems also don't behave this way. Imagine trying to make a risk analysis about some kind of system that could fail, where the probability distribution you pull from for the damage caused has no expected value. How do you even reason about this object? And there are many probability distributions that have this property that they do not have an expected value because the long tail is so fat that it just goes to infinity. How do you reason about an object like this? How do you prepare, defenses or insurance around an object like this? We don't have stable theories or a tradition of scientific and engineering to deal with objects that have properties like this. And my claim is that super intelligent optimizers have these properties, is that you can't do many repeat experiments of them, and you can't model them as a simple thing where you know ahead of time the maximum amount of damage it can do is, say, X, or it can only do X, Y, and Z, and it will never do W. This is not the case with sufficiently powerful optimizers, because by definition, once they're smarter than us, they will be capable of doing things in the universe, taking actions and coming up with plans that we will not be able to come up with ourselves. And we will not be able to model ahead of time. And we won't be able to put any kinds of bounds on what kind of behavior or damage these things could cause. We don't get these properties with superintelligence. This comes from all the standard problems. Optimizers tend to set values to extreme values. We have instrumental convergence. We have the whole stop button problem. All these classic problems in alignment are variants of this. We can't use our normal philosophy of science or normal tools of epistemology to reliably deal with these kinds of scenarios where we have systems that have these extreme properties. You may notice I'm not really making any specific claim about the system is going to be built this way or that way, or it's going to have a desire, or it's going to have consciousness, or God forbid anything like that. I'm making very strong, just simple statements about the way we do science as a species. I completely believe, could a hypothetical, more rational, more advanced alien species deal with this? Yes, absolutely. I think we're already seeing, philosophy of science and epistemology and statistics advancing. And I think if we had more time, we as a species would develop better ways of doing science, better ways of, doing experiments without having to do the dangerous experiments, a better ways to model and reason about Knightian uncertainty and like, black swan type events. But we're not there yet. And this is a problem that requires that to solve reliably, I claim, would require just far more sophisticated philosophy of science than we currently have, far more efficient methodology, far more efficient systems to deal with. And that is why this problem is hard. It's because it is a type of scientific. It's like we go to science 2. We need level 2 science to be able to solve this, but we only have level 1 science. And now we're hit by a level 2 problem. And how do we solve this problem? It's tough. We probably will only get one shot with superintelligence, which is at the core of why it's so hard. If we accept, stuff like instrumental convergence, it seems pretty obvious that if you have a misaligned system, and I expect these systems to be misaligned by default until proven otherwise, that they will be incentivized to take over, to take away power, to not be able to shut down, to gather resources, to prevent retaliation, et cetera, et cetera. There will be no iterative refinement cycle. There will be no attempts where we can try over and over, trial and error, science 1.0 style. We need a whole different approach to be able to solve this problem in one go. And this is just something our species does not have much experience doing. Again, I think this is something we could do. I think this is a thing that a smart species taking its time with enough theory work ahead of time could do. But I'm not sure if we're going to do it. This also leads into the problem with coordination. A sufficiently smart species would be already well coordinated on this problem. Everyone would know about this problem. School children would be taught about the alignment problem, and all the smartest researchers would all go into alignment as the most important problem. And all the hardware manufacturers would, agree to slow down the development of GPUs until we are more certain about what we're doing. But Moloch reigns. Moloch always reigns. Game theory, despite its name, is very not fun and leads to all kinds of difficult scenarios. Coordination is very hard, even if you have two people who completely want to coordinate. Lemon markets are a great example of this. It's very hard to coordinate, especially at scale. And especially when it's dealing with something complicated like this, where we have a profit incentives. AGI systems are going to be the most profitable technology to ever exist. Of course they're going to be. It's not clearly visible how dangerous these systems are until it's already too late. It's anti-inductive to normal progress norms. Especially like Silicon Valley and stuff, there's these beliefs about how, all technological progress is always good. Economic development is good. Scientific progress is good. And I get it. I want to believe that too. I grew up, classic, sci-fi transhumanist, progress guy as well as anyone else. But the problem is hard. And if we don't solve it correctly, it might not be. And of course, it's all a huge unilateral curse type situation, where it just takes one uncareful actor to ruin it for everybody, which makes coordination even harder. Look, I don't know how to say this, but our civilization got its ass handed to it by an evil droplet of fat 2 years ago. How do you think we're going to deal with something that's actually competent? There's a teeny amount of optimization pressure that went into COVID. How many bits of optimization pressure could have maximally gone into COVID? Not very much. And that froze our entire civilization and screw everything up for 2 years. Imagine if we have a system that's actually optimizing against us. I don't think it's going to be a fair fight, so to speak. So does that mean coordination is completely impossible? There's nothing we can do whatsoever? I don't think that's exactly true. I think it's close to true, but not exactly true. I do think small-scale cooperation between, say, OpenAI and DeepMind, yeah, that seems pretty possible. I've talked to people from all of these organizations, and yeah, I disagree with some of them. I think some of them are wildly over-optimistic, but they're reasonable people. You can talk to them. Sam Altman replies to my DMs on Twitter, It's there's a lot of reasonable people out there. But, at large scale, getting USA and China to coordinate to slow down AGI progress, my opinion on that reminds me of the classic parable of the scorpion and the frog. And the story goes that a frog is about to cross the river, and a scorpion approaches. And the scorpion asks the frog to take it across to the other side of the river. The frog says, well, no, you're a scorpion. You're going to sting me. The scorpion says, but no, that would be stupid. If I sting you, I'll drown as well, so I have no incentive to do that. The frog thinks, yeah, makes sense. So the frog lets the scorpion ride on his back, and as they reach the middle of the river, the scorpion stings the frog. The frog says, "Well, why'd you do that? Now we will both surely drown." In which the scorpion utters the immortal words, "Lol, lamau." I think that's how the story goes. And that's my opinion on large-scale coordination as well. Getting USA and China to coordinate to slow down HUI, lol, lamau. So what do we have? So unlike some other people, I do think that some progress has been made about alignment. I am much more optimistic about alignment than I was like 3 years ago. There's been more progress in the last 3 years than I expected to see personally, which doesn't mean it's a lot, but it is something. I think there are some pretty interesting directions that, if they turn out to actually achieve their whole goal, would very much change my likelihood, my outlook, on how likely it is we can make progress on these various problems. But do I think we have a clear path to victory? No, as I've already said. So one of the first class of approaches is agent foundation slash embedded agency kind of stuff. This is kind of the belief that we need formal theories of agency, optimization, decision theory, blah, blah, blah. We have to actually understand systems on a deep, deep theoretical level to be able to extrapolate to these very powerful systems, have very strong formal guarantees about why we believe certain things to extrapolate or not. And I think this is probably the right way to approach the problem in the limit. If we want to reason about extremely powerful systems, one of the only ways we have to do that reliably is through mathematics and through formal theories that we have strong guarantees on, and we can think about provability and so on, if we had enough time. So one of the main problems with agent foundations is that it's really, really hard. And it's very hard to even know whether we're making progress or not on this kind of things. This whole approach is kind of spiritually kind of started by Miri, and they've written a wonderful post called Embedded Agency where they kind of explain some of the open problems and why it's important. It's a really lovely post. I really recommend you read it if you're interested, kind of justify some of these problems and such. And I think this is really interesting and really important. And if I had long timelines, this is what I would be working on. But yeah, unfortunately, I don't know if we're going to have the time. And also, I don't know what's the deal with Miri right now. They seem to be going through a bit of a crisis at the moment. So there's still some work happening there, but I'm not exactly sure what the scenario there is. But there's two approaches that I would like to talk about, that I would like to highlight as I think particularly interesting directions toward in the agent foundation kind of direction. One is the natural abstraction hypothesis and selection theorems. So this is John Wentworth's agenda, and I am super excited about this. This is some of the things that have updated me to be more, to think that more progress has happened over the last couple of years. I've seen John Wentworth into the field and some of his approaches. I find these so interesting. Then I'm kind of lumping two together here. So the first is the natural abstraction hypothesis, which is kind of like this hypothesis that different algorithms trained on the same data tend to have the same abstractions internally. So an example here is, say you have a neural network, an unsupervised neural network trained on images, like reconstruct images or something like that. Very often, if we train such a network on natural images, they will have one neuron or something that encodes the concept of tree. You never labeled, to be clear, the concept of tree. You never forced it to learn this concept. They just tend to often naturally pick up on this, which is pretty interesting. It makes sense in some degree that, there's just some abstraction, trees are a obvious kind of object. But I think there's kind of like a background assumption, an implicit assumption that most people make, that the kind of ideas, concepts that we humans have in our head, like I have chair and desk and computer and stuff, are kind of arbitrary. But the natural abstraction hypothesis argue that maybe not. Maybe that is actually not at all arbitrary, and there's something about the environment that makes certain abstractions natural and more likely to be used by systems working in similar environments. He has a lot of much more interesting, theoretical reasons to believe that there's things in this direction. He is very optimistic about this. He is optimistic in the degree that he thinks we will be able to, in the future, take, say, neural network systems and compute out all of the abstractions it uses internally and reason about those externally. I am much more pessimistic than him that this will work, or rather, I think it probably will work, but will be computationally intractable. But he seems optimistic. And I think if this turned out to be true, especially for like interpretability and stuff, this would be incredibly good news. If networks just tend to naturally have internal concepts that we can point to about humans or about values or about the environment or such, might be extremely powerful for aligning them. A somewhat related direction is what he calls selection theorems, which is kind of a mathematical direction to think about what kind of properties do optimized systems tend to have. I really love how John explains how he came up with these in the first place. So it makes intuitive sense. Why would this be used for alignment or like AI, right? If we have like reasons to believe that systems when trained will be, I don't know, modular or non-modular or whatever, that seemed like a really useful thing to know about them. But I like that his reasoning is that he came from biology, and he thinks the reason biology is kind of like stuck in a rut and having so many difficulties with reproducibility and stuff is that biology is the science of reverse engineering optimized systems. We have systems that were optimized by evolution, but we don't have a theory of what properties optimized systems tend to have. This again brings back to like this like science 2 kind of thing I was talking about earlier. Is that with science 2, we would have a whole science of complex optimized systems. What kind of properties they have? If you give me an optimizer and a goal, can I reason about what kind of systems this thing would build? So I think this is a really interesting direction. It's very theoretical, but still with enough connection to practical results that I think is both very understandable. John's a very good writer, and very clearly, if these things turn out to be true or useful, this would very much update my probability that things are going to go well. I'm a big fan of these approaches. I highly recommend you read some of John's stuff. He's also really nice. He's easy to like ask questions or reach out to if this is something you might be interested in working on. This is definitely one of the things I am most excited about of all the methods, of all the directions I'm going to talk about here. Another direction is the learning theoretic agenda or informationism. This is Vanessa Kosoy's agenda. And to be quite honest with you here, I do not know enough math to really understand this. From my understanding, it is a way of generalizing probability theory to kind of imprecise probabilities. It allows you to reason about probabilities in a more general kind of way. So Bayesianism is great, but it makes some really bad assumptions, such as logical omniscience. So it assumes that you know the consequences of all of your data, which of course cannot possibly be true in a natural system. And also it has the grain of truth assumption, where Bayesian reasoning assumes that the true hypothesis, so the true generating function of the universe, is somewhere in the hypothesis space. But this obviously cannot be true because you are in the universe. So you can't have a model of the entire universe, including yourself, inside of yourself, because you get into like a recursive problem there. So infrabayesianism allows you to reason about systems more generally. This is a horrifically mathematically complicated thing. Like this is some intense shit. This is stuff that goes well beyond my undergrad level understanding of mathematics. But the parts I understand are definitely very interesting. It definitely seems like a worthwhile thing to think about. How do physicalized, embedded agents who can't model all of their environment, what are they capable of modeling? How much can they think about their environment? How do they make decisions in this kind of imprecise probability way? It seems like a very promising approach. It is worth mentioning, though, that it also feels like it might be a bit nerd snipey. It's like very beautiful mathematics. It has like, incredibly cool theorem proving. It's like really rigorous and elegant and all this kind of stuff. And it's unclear how much this will be useful or not. Vanessa obviously thinks it's useful, and I mean, Vanessa's smarter than me, so that's definitely should count for something. And a lot of other people also find it very interesting. But my view on this is basically, if you're the kind of mathematician to be nerd sniped by this kind of thing, that hears stuff like SA measure and ultra filter and other horrifying topology and measure theory type stuff, and thinks, hell yeah, maybe this is a good thing to be nerd sniped by. So if you're the kind of mathematician that would love to work on this extremely intense mathematical stuff, as far as last I've heard, they're currently hiring for more researchers. So if this seems like something interesting to you, I would love to see this theory more developed. And if there's anyone out there who happens to be this good at mathematics to understand it and also explain it, good luck. Because like 5 different people have tried. I've read all their explanations. I still don't really get it, but it's worth a try, I guess. Now, the more common approaches, I think, nowadays, are the prosaic approaches. So this is the kind of belief that working with these kind of different approaches that work with current tech level systems, things that work on neural networks and try to train them or empirically think and work with these kinds of systems. A general assumption here is that AGI will in some ways be similar to the systems we have today. So by studying the systems we have today, we will be able to learn things that will be relevant to more powerful systems. I personally think this is a completely reasonable assumption to make. So I have very, very short timelines. I expect AGI to happen very, very soon. And therefore, I also expect AGI to fundamentally be a neural network, probably running on NVIDIA GPUs. Sure, it might have a slightly different architecture, might have had a different training objective or whatever, but I expect lots of the principles we have now to translate almost one-to-one to AGI. There's already a lot of very interesting things we can study using the systems we have today. But even if not, I think it's kind of unlikely that the work you would do on this nowadays will be completely useless. Some people are really worried about this, especially people with longer timelines. They're worried about, I'm not going to work on alignment right now because we don't even know what AGI is going to look like, so the work I'm going to do is going to be completely useless. First of all, I think that's really bad reasoning, but that aside, I don't think that's probably likely to be true. There's an illustrious scientific history of the success of the method of staring at an object of interest really hard. And I think this is very underrated in many modern circles, that just studying the object, looking at it, doing experiments as much as possible while you still can, is an important way of making progress in scientific method in a scientific field like this. Is it the way that's going to solve us all the way? I don't know. Maybe, hopefully. The big question here is, how much will it scale to AGI assign? Again, we have a substitution hazard situation where you have this hazard of potentially, making progress on aligning a very weak system and think, oh, well, my method works on a very small system, so I made progress towards the hard system, even if it reliably, you can already predict ahead of time, this cannot possibly work with a stronger system. Speaking of which, RLHF. So reinforcement learning from human feedback, RLHF, I'm also classifying recursive reward modeling into this, is a very common, very popular approach right now, especially in labs such as OpenAI and Anthropic, is a very common approach right now, a pretty straightforward kind of approach. And so I've been asked what my opinions on these methods are. And I guess the best way to summarize my opinions is hilarious laughter followed by gurgling sounds as I'm consumed by paper clips. I'm joking. But, hear me out. So RLHF in its most naive form is a method where you train a model to predict human judgment. So you have human judgment rating various inputs and outputs, whatever, as good or bad, and you have some model that tries to model this human feedback process and then control some kind of policy network in order to produce more favorable outcomes. And this works great with current systems. This is a really nice method. It's tricky to get working. It's very finicky, as RL always is, but it's a lovely method. I know you guys have tried InstructGPT or something, but it's really cool. It's really good, and it works much, much better for most tasks than other GPT models do. But this naive way cannot possibly scale to SLI. I claim, at least. I think some people will claim it might. I really don't think that's the case. If you have a system that is just modeling human feedback, first of all, it's never going to do this, robustly. So you're going to run into good hard. You're going to have your super intelligent model is just going to good hard the proxy and do something crazy. We already see this happen with many systems, that if you let it optimize too hard, it just produces random strings of characters that for some reason trick the reward model and make it output a really high reward. And also, even if it would perfectly model human feedback, that would still be bad, because the super intelligent system would just reason, well, this human feedback process is done by a human, which is out in the environment, and the best way to maximize feedback would just be to take over the human, or something of the sorts, to break out a simulation, couldn't take control over the rating function. So even if you somehow had a perfect proxy, it still wouldn't work. So there are some methods, such as debate, that fall into this general vicinity, but might scale better. So they use RLHF as maybe one building block in a more complicated algorithm. I think it's possible that there are directions here where RLHF or RRM will be useful and maybe actually can scale. The naive version obviously can't, and I think most people also at OpenAI and stuff probably agree that that is the case. Um, but I'm not super optimistic, even about stuff like debate and stuff. I'm more optimistic. I'm not maximally skeptical about it. I think it's something worth looking into. I think it's worth something some people should be studying and trying. How good does RM and debate scale and stuff? Definitely seems like something someone should be doing, but I'm not very optimistic about this stuff. And I think of all approaches, this one has the strongest substitution hazard, and it's very easy to see your instruct GPT, getting great user ratings, and you're like, oh, we've done it, boys. Alignment is no more. But that is a very dangerous assumption to make, and this leads to the whole like unilateralist curse type situation. So, is there something here? Maybe. Should some people be studying it? Yeah, probably. But be very, very careful of substitution hazards when working on this stuff. Don't get lulled into a false sense of security just because you got GPT-2 to do what you want it to do. You have to have an additional argument, an additional reason to believe why these kinds of methods would scale to larger and more powerful systems that may be able to take actions that you couldn't predict. Another interesting approach is called relaxed adversarial training. And so here's the problem set up. You have a model which is deceptive. So it's trying to break out, it's trying to, screw you over, whatever. But the model's clever. It knows, well, if I'm in training a simulation and I try to break out, well, my handlers won't allow that. So instead, it uses internal circuitry so that only when it sees a valid Bitcoin blockchain dated 5 years into the future will it become deceptive. So that means you would deploy it or whatever, it would go fine. Then 5 years later, a certain block is minted on the blockchain, and suddenly, it turns deceptive. This is like a version of the RSA 2048 problem. A solution might be, well, we could use some kind of method to show it the concept of a valid Bitcoin blockchain dated 5 years into the future, because we can actually generate a valid Bitcoin blockchain dated 5 years in the future, because that's computationally hard. You would have to solve, we don't have enough computing power to generate this thing. So the general problem that relaxed adversarial training is solving is that there are computationally hard to generate observations, inputs that are just computationally hard to generate, that might make the model behave differently, but the model might know would exist in the wild, and then cannot be in simulation. So there's a way for it to know how whether it's in simulation or not. Kind of, it's like one thing. So if we could do this, this would be great. This seems like a great idea. We could catch a lot of failure modes this way. This would be a really useful method for training it to not do many things we might not want it to do, even if we can't generate an example of every single time. One small problem, literally no one has any idea how to do this, or if it's even possible in principle. Some people seem to have some ideas, some directions, which maybe are related to something, and some people are pretty optimistic about it, like Paul Cristiano and I think Evan Hubinger are kind of optimistic about this kind of directions. If someone can figure this out, I think that would be great. If this kind of methodology would work, I kind of expect this doesn't work in the general case. So I'm not super optimistic about it, but some smart people are, and if they get it to work, I think this would be a great thing. Then there is almost the obvious direction, which is interpretability / ELK, or eliciting latent knowledge, which is Paul Cristiano's kind of direction for how to trying to study how to get information out of a network. I think everyone agrees that this is almost definitely good, or at least worth trying. It's worth trying to understand our neural networks, open the black box. What are they thinking about internally? What do they know? What are they capable of? Etc. etc. This seems obviously good to try. There are some downsides I can see, but it seems pretty clearly on the Pareto frontier and from one things to try. I do think there are a ton of low-hanging fruits here, but I think the main problem with the scaling here is what we see in this kind of graph is that simple models are really easy to interpret. They're very simple. There's not many moving parts. Then as they get a bit stronger, we get this valley of confused abstractions. We have these really weird polysemanticity. They don't really understand the world. They don't really have clean abstractions or something. Then as these models get stronger, they seem to get crisper abstractions. This is kind of what we're seeing with larger models. They often have more disambiguated neurons and such. I've been surprised how much interpretable stuff there is inside GPT or something like that. It doesn't mean it's definitely going to be totally human interpretable. It might just be not. It might not be possible. But unfortunately, I think it's pretty probable that as these systems become even more powerful, they eventually reverts or we have systems that use abstractions that are so complicated, that are so insane, that we humans can't possibly understand them. This is something where the natural abstraction hypothesis would probably change how this curve looks. Is that maybe the natural abstraction hypothesis, if it turns out to be true in a strong sense, would make us believe that even the very powerful systems would be more understandable to humans. Or not. It definitely seems like something worth trying. I do think there are downsides to work on interpretability as well. I once talked to someone who worked with the military in the USA, and he said the number one thing holding back the deployment of neural networks in military is interpretability. Justification of why these networks make the decisions they do. So that's terrifying. And also, I think it's quite likely that when we study these things in a very deep level, that we will also uncover capabilities increases. We will see bottlenecks that these networks encounter or bugs that exist inside of them, and we'll be able to fix them. So it's not as clear to me as it seems to some other people that this is always going to be a net positive on alignment only, but also capabilities. But to be fair, I personally think that most alignment work is sort of capabilities work as well. Just something to keep in mind. But overall, if I could point smart engineer types to one direction of work that's obviously at least worth trying, interpretability would be the direction. And I think there are a ton of low-hanging fruit here that someone should try. And I've seen again and again people coming into the interpretability field and just looking really hard at their models and very often finding really interesting and useful things. So this is definitely something I strongly recommend working in as a very promising field. Then it's a little something unusual, which I'm kind of call simulator theory. So this is something that we're doing in Conjecture, which is my alignment startup. And simulator theory is it's a bit funky. It's a different scientific frame, is how I describe it, to think about GPT models. I think a lot of people tend to think of GPT models as kind of like an agent that you talk to, some kind of as a utility maximizing agent. It's like the default way we use to model intelligent systems. But we would argue that a better way to think about GPT is as a simulator of text generating processes, which we call simulacra. And we think this view is very promising to give you a different view of these systems, to bring different questions. You think of them as these simulators, or also as priors over agents, or even multiverse generators, where you have these different timelines, world lines, different ways the prompt can continue, and you have a probability distribution over these various lines. And we think this is other than just being cool and aesthetically pleasing, we think this is very interesting, that it leads to non-trivial implications for alignment. Like, what properties do we expect these kind of systems to have? Will they be optimizing in the same way that normal agents do? Do they have other safety properties or capability properties that might be interesting? We think there's a lot of non-trivial work to be done here. It's kind of like looking at the same object from a different perspective. It's like, we can look at fluid as particles, or we can look at it from the perspective of fluid dynamics. You have different formulas, you have different theories describing the same object, and different theories will highlight different parts of the object as worth studying. And that's kind of how we think about simulator theory. It's a different perspective on GPT type models, which will highlight different questions. Will this lead to something really useful? Fuck if I know. Maybe not, but sure is worth trying. It sure is interesting. And we will be, So Eliezer said he couldn't completely dismiss all of our theories. He sure as hell tried, and I think he thinks he dismissed all of them, but we think he didn't. And we have several things we're betting with him on. So that's definitely promising. And we will be publishing more about this hopefully very soon, where we're going to do introductory to simulator theory and explain why we think this is a promising approach. And hopefully, once we get our experiments running, we will also have some bets with people like Eliezer to show whether our theories are right. It's quite amusing when he visited lately. There was a few moments where he said, something would be, X would be completely impossible. And me and Kyle, one of the people working, kind of looked at each other and were like, we could probably do that in 24 hours. So we'll see who's right. Definitely interesting direction if you're interested, and stay tuned for this. So, what now? I've talked to you about why the problem is hard. I've talked to you about the approaches we have right now. But now what? I mean, other than the obvious, I think if we need to roll high, roll many dice. I don't think we have clearly any approach that we just have to, we just have to buckle down. We just need to fund this one project. We just need to program this system or something, and then the problem is solved. I think we need to get lucky. We need to roll many dice and find breakthroughs. And this is untypical. This is how science usually works, right? Lots of people come at a thing from different directions, and eventually someone finds the breakthrough. I think it is hopefully not controversial to say that there should be way, way more people at least trying to solve this problem. Like there's like what 200 people in the whole world maybe working full time and trying to solve the alignment problem. That's ridiculous. This is like the most important problem in the world, and that's all we've got. Yeah, it's a bit unfortunate. We should try many, many approaches. We should come at things from different angles and hope for a breakthrough from an unexpected direction. I think it is possible, but as I said before, I'm not optimistic. I have very short timelines. I'm honest about that. I don't expect this to go well. I think something crazy has to happen in the next couple of years in order for this to go well. And that can happen. Crazier things have happened in history. Crazy things happen all the time. But we do need to try many different things. We need many more people trying the problem, coming at things from different perspectives, having different perspectives, trying their own theories, or work with someone else's theories, or going off in completely different directions, or big mega teams coming together to work on one specific approach, or whatever. Whatever we need to do is we need more people trying to think about the problem. That's my number one thing I would advocate for. There are also bottlenecks that are not strictly research that may also contribute much, which I think is also worth keeping in mind, such as ops roles in alignment organizations, really important stuff, and also fundraising and various kinds of just like normal engineering or design work can be really important. This kind of stuff. So don't count yourself out just because you don't consider yourself a researcher or a genius mathematician. There's a lot of work to be done, and a lot of things that are worth trying, and we've barely scratched the surface in what is possible and what we should be trying. So thanks everyone for coming to my talk. I would like to just show my company 1 second here. Conjecture is hiring. We are an alignment startup working on hopefully incubating many different approaches to the alignment problem. We're currently a bit biased towards GPT kind of prosaic research, but it's not the only thing we want to work on. And we are far from maximally stupid, quote Eliezer. So we have that going for us. So thanks everybody.